Thanks for the introduction. So, good morning. I'm impressed you all make it, but okay, I appreciate we start at 10. Otherwise, I would struggle. Okay, so the topic of today is the stochastic gravitational wave background. I'll say in a minute, I'll say a bit more what I mean with that. So this is really getting us now towards the cosmological sources as opposed to the black hole mergers we were discussing yesterday. So briefly, just to recap what was important from last lecture and what we'll need again. So the gravitational wave equation, right? By now, you should recognize it. Now comes the day where I've lost patience, right? And I set C to 1. We're still keeping G for the moment, right? Though we may also lose G at some point, but let's drop C. Importantly, we estimated yesterday the energy density in gravitational waves. We discussed, okay, it's the 2-point function of the time derivative of the gravitational wave, and we discussed in quite a bit of detail what these averaging brackets here mean. And this energy density is really what we talk about when we talk about stochastic backgrounds, because that's basically the physical quantity that is a property of the stochastic background. And then we also, just for completeness, we won't actually need that today, but we'll need it later. We estimated how we can compute a gravitational wave in the TT gauge in the far field limit emitted by a source which has a time-dependent quadrupole moment. So the topic of today is the stochastic gravitational wave background. And this is very different to the types of sources that we discussed yesterday, right? So the idea here is you are sitting here on Earth, you have a detector, and now you are observing a whole bunch of gravitational waves which are coming to you from all sorts of different directions, with all sorts of different frequencies, with all sorts of different phases. Now, where could those gravitational waves be coming from, right? So they could be coming actually from black hole mergers, right? Imagine you have an instrument like LIGO, right? It's sensitive to, say, a certain volume in space. Within this volume, if you see a black hole merger, you will actually resolve the waveform, right, that we saw yesterday, and you will measure it, and you will say, aha, I've seen a black hole merger. But for every merger that you kind of see within this detector volume, there'll be a ton of more mergers which are out here, which have a too low signal-to-noise ratio to be measured individually, right? But there's a lot of volume here, right? So you'll get lots and lots of things coming everywhere here from the outside. You won't be able to resolve it individually, but it will contribute to a background noise in your detector. Yeah, you'll get a bunch of kind of unresolved gravitational waves, which are just contributing in an incoherent way in your detector. So you won't be able to resolve them individually, but you will see some sort of signal of this in your detector. So that's one way you could get this. The other way you could get this is that you can think of this sphere here not as kind of the limit of your detector volume, but you can think of it as an event in cosmic time. You can think that there was, at some point in cosmic history, something happened, something violent, right? Something with a large anisotropy, say a phase transition with bubbles colliding and all this. And at this point in time, right, and a point in time in the expanding universe translates to a sphere as seen from the Earth. At this point in time, a bunch of gravitational waves were emitted, and they are then detected on Earth sometime later. So the first picture is more the astrophysical idea, how astrophysics can give you a stochastic gravitational wave background. The second is the cosmological idea, right, how a cosmological source could give you a background. And the second idea, so the cosmological one, is very close in spirit to what we know from the CMB. Okay, in the CMB, you have an event in space-time. It's the decoupling of the photons from the thermal bath, right? We perceive that as a sphere in the sky, right? Isotropic radiation coming to us from a certain distance, right? Which corresponds to a certain time when these photons decoupled. And then we observe in a detector a diffuse noise of these photons. Okay, so now, of course, we have Planck. We can see beautiful things at the CMB, but that's not how it started, right? The CMB, when it started, was Penzias and Wilson building a radio telescope and having some diffuse noise in there that they didn't understand, that they couldn't get rid of, right? Some irreducible noise that they were wondering, what the hell is this, right? And so now this type of noise is what we would like to see with gravitational wave detectors, right? So in some sense, we're pre-Penzias-Wilson, right? Or maybe at Penzias-Wilson, and we're trying to see this diffuse noise of gravitational waves coming from everywhere in the universe. And once we see that, same as with the CMB, right, we'll have to distinguish in CMB language foregrounds from backgrounds, right? So in the CMB, you know, you have all the galactic sources, you have diffuse light everywhere, right? That's a foreground. It's photons, all right, right? But it's not the photons you're looking for. And same here, right? You have you have a bunch of gravitational waves, which are gravitational waves, but then maybe if you're a cosmologist, they're not the gravitational wave you're looking for, right? Because you're looking for the cosmological ones. So you'll want to be able to distinguish the astrophysical contribution from the cosmological contribution. Now, if you talk with an astrophysicist, they will say, this astrophysical one is the foreground and the cosmological one is the background, right? So that's a matter of what you're interested in. But there are two contributions a priori, right? So there can be the Cosmo one and the Astro one. Roughly what we expect is it should be somewhat isotropic, though it doesn't have to be perfectly isotropic. Should be probably somewhat Gaussian. And probably somewhat unpolarized. Simply because we have superposition of many, many different things arriving in an incoherent way, right? So this is roughly what we expect. And it's really noise, right? In your detector, the way this shows up, exactly the same as for the CMB, will be as an additional noise component in your detector, right? So detecting it is a lot more difficult than detecting an individual event, because this thing is never off. Okay, you cannot shield it. You cannot turn off the universe. So this is kind of a noise component in your detector, which is always there, but which you convince yourself is not instrument noise. Okay, so this is really kind of thinking the way Penzias and Wilson discovered the CMB. They saw a noise source. They did everything they could to remove all possible instrumental reasons for having a noise source, all possible environmental reasons for having a noise source. And only once you're absolutely sure that everything is super under control, right, then you think maybe you've actually measured physics. And that's the same challenges we will be facing here if we want to detect such a thing. Yeah. 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 Right, so I would compare the CMB I mean, it's not, as always with analogies, right? It's not perfect, right? But I would say the CMB decoupling, right? Not the sourcing of the photons, right? But the CMB decoupling is an event in cosmic history after which you have free streaming photons. A cosmological phase transition is an event in cosmic history which sources a bunch of gravitational waves, which are then immediately free streaming, right? So in both cases, you have an event in time, and after that event, and not beforehand, you have free streaming particles. In the gravitational wave case, beforehand you don't have them because you just don't have the source, right? And in the CMB case, you don't have them because they're not free streaming. Okay, so that's the goal of today, right? We want to understand, so how do we describe this stochastic background? In particular, the one from cosmology. Because the one from cosmology is, of course, the one that we then want to use to probe the early universe, probe particle physics, learn about physics beyond the standard model. So we want to understand how we even describe this properly, and then we want to understand how we detect it. Which means, so far we've most of the time worked in flat spacetime, Minkowski spacetime. So now we're doing cosmology, right? So we really need to go to FRW universe. So gravitational waves in an expanding universe. So what you need to do is, when we started off with Einstein equations, and we said, okay, we do a perturbation flat metric, Minkowski metric, plus h. And now basically what you need to do is you need to go through that entire exercise again, but instead of perturbing around a flat metric, you perturb around the FRW metric. We're not going to do it all again, right? Because, fundamentally not much changes. I'm just going to give you the final result. And also when we did the decomposition in the degrees of freedom, right, we already had the scale factor in there, right? So we already know there nothing changes. So it's really the question of how this first equation on that upper board, how that changes if I perturb not around a flat metric, but I perturb around the expanding universe. So the metric that we're interested in is minus dt squared scale factor dxi, or we'll sometimes also use conformal time, where we put the scale factor all the way out front, and then we just have d tau squared minus dx squared, right, where this is dx squared. And if we perturb around this metric instead of around the flat metric, what we get for the wave equation for the gravitational wave is we will get, again, the box operator. And then we will get one new term, which is 2a prime. Okay, so dot will be always derivatives with respect to cosmic time, and prime will be derivatives with respect to tau, conformal time. Here, by the way, is your friction term that somebody was asking about, right? And the right-hand side is unchanged. Okay, so you immediately see if you put them back in flat metric, scale factor is just 1, a prime is 0, this term disappears, right? And you recover the result from before. And so the new term is this guy, 0 in the static universe. And now we need to understand how this guy modifies kind of our understanding of what the gravitational wave actually does, right? What does this term do in a wave equation? To do that, we'll go to Fourier space, because everything is linear. We go to Fourier space. Once I'm in Fourier space, right, because I have a defined k vector, I can immediately decompose into the polarizations. So I will decompose into the plus and cross polarizations. And I will also introduce, for notation, another object, h tilde, which is a times h. 8 times h bar, to be specific. Yeah. No, I hope I didn't. No, conformal time, tau, right? So this is d tau, where tau is defined here as conformal time. Yeah. No, we're in Lorentz gauge, right? But we're not in TT gauge yet. We will go to TT gauge, but we're a priori, this is the general equation, right? Here we've imposed only Lorentz gauge, not TT gauge, which is why we still have the bar. Yeah, but very soon we will go to TT gauge, because we want to, now we're doing cosmology, right? So we're in vacuum the whole time. So TT gauge is completely sufficient. We're not dealing with stuff inside sources. Yeah. The new term just came from, instead of doing the same exercise we did in the first lecture, but not expanding around Minkowski metric, but expanding around FRW metric. So it's a fun exercise to do. if you have some time in the evening, I don't know, if you have energy, you can check if you get the term. Okay, so this is just change of variables. Go to Fourier space. So we'll get from the box operator two time derivatives plus the k squared term. This guy becomes just imposing this, just using this relation here, minus a double prime over a. And here there's an extra factor of a simply because I've multiplied the entire equation with a to get this. And here we have the energy momentum tensor, which is also in Fourier space. I'm giving it an index lambda, which just indicates we've taken the full energy momentum tensor and we've projected it onto the relevant polarization. Okay, so this is essentially the projector operator that I was showing you beforehand, just now projecting directly onto the plus or the cross polarization. But very soon this will be zero, right? So then we don't mind. And now you can show that this guy, just use Friedmann equations. This guy is a very good approximation. It's just what the leading order in the slow roll parameter. The leading. Yeah, in FRW is exact, right? So this guy is essentially AH squared, right? So the co-moving horizon, which tells you that this is the new term, right? This came from here. So it tells you that we can look at two limits. We can look at the limit where k is much smaller than AH, and we can look at the limit where k is much larger than AH. And the physical meaning of this is distinguishing subhorizon and superhorizon scales. So, because the Hubble horizon in cosmology is roughly the causal horizon that you have at any given time. So now the question is the gravitational wave you're discussing within this causal horizon or not? So the more intuitive case is a subhorizon case, so small scales. So k much bigger than AH. H, so just H, right, is the Hubble parameter, so A dot over A. So this is subhorizon, small scales. Okay, so in this case, we just drop this term here, right? So we just get H tilde double prime plus K squared H tilde. And let me now look at this in vacuum, right? So then this is just zero, because I'm interested in describing the propagation of these waves in this limit. But this is just a wave equation, right? So now you see from here that the solution to H tilde is just some plane wave, right, some cosine. And hence the solution to H, which is the thing we initially had, is just that wave divided by A. Okay, so we just get that H bar is something cosine omega t divided by A. Where, I mean, I've just dropped the indices, right? I mean, this is index lambda, right? And then you have some polarization tensor here. But what this tells you is that it's kind of more or less what you expected, right? If you're on scales well inside the horizon, right, then you can nearly neglect cosmic expansion, right? You just get an oscillating wave just as before. The relevance of having the expansion is that the amplitude decreases with 1 over the scale factor, right? Which means if you source a gravitational wave in the very early universe, you can think of it as being diluted, right? And you can think of it that if you want to detect it much, much, much later, due to cosmic expansion, that has become harder because the amplitude is decreased with 1 over the scale factor. The other limit we can look at is the opposite, right? So the superhorizon limit. So in this case, it's actually easier to go back to that equation to see what's going on. So in that equation, since now k is very small, right, we're going to drop the spatial derivatives in the box operator. So what we get is that AH double prime plus 2A prime H prime is 0. Okay, so again, I've set T mu nu to 0. I've taken this equation, I've multiplied with A. Oh, yes. Thanks. Yes. Superhorizon, large scale, small k. Thanks. Okay, so this is now a differential equation for H, right? You can plug this into Mathematica. You can ask what is the solution. The solution is that H will be some integration constant. Let's call it A lambda, plus another integration constant, because this is a second order differential equation. Integral 0 over tau d tau prime A of tau prime squared. Okay, now you're like, okay, well, that didn't do much, right? I mean, that doesn't help. It does help. It helps because in any expanding universe, right? So radiation domination, matter domination, even CC, this thing goes to 0. Right? So maybe initially this term had an effect, but now I expand my universe and this term will always die out. Which means that the solution is given by the integration constant. Okay? So what does that mean? That means that if I have that the gravitation, and in particular nothing is oscillating here, right? So this means that on superhorizon scales, the gravitational wave is just a constant. What value that constant takes depends on the matching conditions, right? So say you have a gravitational wave which you generate during inflation, then it gets pushed outside the horizon. Outside the horizon will be constant. Which value does it take? Well, it just takes whatever value it had at horizon crossing. And this is what we mean when we say, and I'm sure you've heard this last week, when we say that gravitational waves, or also scalar perturbations, are frozen outside the horizon. Right, so frozen. In particular, they don't decay as 1 over A. Right, so you can, say during inflation, you can source a gravitational wave, you can expand the universe, push that outside of the horizon, and then it's in the freezer, right? It's just stuck there, can be stuck there for 13 billion years, not decaying at all, and then only when it comes back inside the horizon, it starts oscillating, and then it starts decaying, right? So, but that's an excellent way of probing inflation, because you kind of had an excellent storage place for all your quantum information. So fundamentally, it's just very simple. It's the same thing basically happens for scalars, right? So, but now for the gravitational wave case, what we, yeah. This is H. Yes, we can put bars. Well, okay. Now since I'm using the polarizations, I guess I'm kind of in TT gauge, right? Okay, let's go to TT gauge, right? So let's go here to TT gauge. We can do this also in a proper detector frame, but there's no reason to, right? So let's say this is general, and here let's go to TT gauge. Because also now, anyway, we're setting the right-hand side to 0, right? So once we set the right-hand side to 0, I mean, going to TT gauge is no problem. Yes. Yeah. So here we've just solved a differential equation, right? So it's just an integration constant. This equation doesn't tell you what is the integration constant. You determine the integration constant by imposing that they have to match. Yes, exactly. Yes, yes, yes. Well, no, it's actually tau, right? Because this is, yeah, it's tau because this was the double derivative with respect to tau. Yeah, yeah, yeah. A shrinking universe. Well, if you had something, I don't know, like a bouncing universe, right? Which, I mean, you need an equation of state which allows a shrinking universe, right? So it's not in the standard model of cosmology where we have radiation, matter, and CC. This always falls off, right? But if you have a general equation of state, right, in particular you have a shrinking universe, then you can check, right? When you just kind of write the scale factor just as some power of time, right? Which is with a scale factor, and then you can see in which case this over time decreases or increases. Any other questions? Okay, so with this knowledge, we can now go along and write down essentially just a reparametrization of a gravitational wave, but one that will be particularly useful. So a useful parametrization for discussing cosmology. And now we really go to the TT gauge, right? So Hij TT at some point x and tau is going to be sum over polarizations, Fourier decomposition, so integral over k. There's going to be, okay, let me leave a gap. There's going to be a polarization tensor, Hij lambda k hat, right? So this is the guy which basically, so say you have the gravitational wave going in z direction, right? This would just be the one that we had on the board the other day, right? I'm sorry, like this. So it would be either 1, -1, 0, 0, 0, 0, 0, 0, right? Or it would be, for the other polarization, this guy, okay? This is for the gravitational wave in z direction, giving you the matrix which has the polarization information. If you have the gravitational wave going in a different direction, right, you need to rotate these matrices, okay? But that is what the polarization tensor does. And then we will have the exponential from the Fourier transformation, minus I k tau minus kx. Okay, and now what am I missing? What am I missing is just a Fourier coefficient. And now what I'm going to do is I'm going to split, using this information that we have here, split the Fourier coefficient into two parts. One h lambda from k, which depends on k but not on tau, and one tk of tau, so something that depends on k and on tau. What I want these things to be is I want this thing to carry the primordial information of my source. So this carries the information. This is basically a snapshot of the gravitational wave spectrum or the gravitational wave decomposition at the time when the gravitational wave is sourced or at the time when it enters the horizon. Okay, so this is the Fourier coefficient at t is tau star, and tau star is either the sourcing time or horizon entry. right? Meaning for any source which is post-inflation, it's just the sourcing time, no complication. Any source that is during inflation, right, so super horizon sources, it's then just the time when it enters the horizon. And this guy is what we call the transfer function. So this takes my primordial gravitational wave and evolves it over time. And the reason we can split it off in that way is that we understand that the time evolution simply scales with a scale factor subhorizon, but it stays constant superhorizon, right? So this transfer function is nothing else than A of tau star divided by A of tau, right? And it has an index k because potentially this value of tau star, which is the horizon crossing, can depend on k. If I'm just looking at a source post-inflation, so tau star is just a sourcing term, right? Then you can drop this in xk, right? Then this just depends on k and this just depends on tau. And the reason I can split it like that is because of the physics that we discussed beforehand. Okay, questions on this? I can split it because I know that on the evolution on subhorizon scales is just that I have my usual plane wave, which decays as 1 over a, and on subhorizon scales, it's constant, right? So once I've distinguished between super and subhorizon, how this depends on tau is in a trivial manner. I know the trivial manner and I can scale it out. It's at the stage which, again, if it's a source, if it's a super horizon source, then it's the coefficient at some time in the super horizon. It's the coefficient at the time when you re-enter the horizon. But since everything is constant, right, it's also at any arbitrary time while it's super horizon, right? Because nothing changes super horizon, right? So if it's a super horizon source, these are just kind of the coefficients somewhere in the super horizon limit. Doesn't matter when you use it. And if it's a sub-horizon source, it's the coefficient at the time of sourcing. You mean here, what is my argument? This will be tau x. Right, but basically we've dropped the spatial derivatives because we're in this limit. Right, so the box, if you're thinking, okay, we're in real space, so you can think in Fourier space, right? If you think in Fourier space, right, then the spatial derivatives are just a k squared, right? And then you can drop that. Yeah, in fact, it doesn't matter, right? I mean, since we're dropping the k squared part, right, it doesn't matter. You can do this in real space or in Fourier space, right? It doesn't matter, right? Because we've dropped the spatial component. Yeah. K tau. So k, exactly. So this k, right, is just absolute value of k vector, right? So that's just omega, right? That's just because I'm traveling with the speed of light. So that's just the usual. I mean, this entire thing is the 4 vector, right? Kx. Product of the 4 vectors, k and x. Just I'm doing the Fourier expansion all the way. Exactly. Yeah, exactly. It's not constant, right? Because there's the tau here. Right? The scale factor depends on time. And so for subhorizon, for super horizon modes, right? No, but okay, so this is the thing how you define this tau star, right? So I'm defining tau star as the moment, I mean, I'm just kind of notation-wise putting two cases into one, right? So I want to define tau, so okay, maybe I should put a theta function here, something like tau minus tau star. So yes, the transfer function, I want the transfer function to be constant on superhorizon scales, right? Yes, but that's just a Fourier decomposition, right? I mean, if you want, I mean, that's just that just really comes from doing the Fourier expansion, right? You can also take, yeah. I mean, you can, it'll be in the coefficients, right? You can take a constant function and do a Fourier decomposition of it, right? And you will just get the k equals 0 mode, right? You will. Okay. So now, okay, so now we understand how we decompose the wave, right? We also understand that if I have a situation like that, right, where I have gravitational waves incoming from all sides, incoherent, subthreshold, right? I'm not going to talk about waveforms. I'm going to talk about energy. I'm going to talk about the energy deposited in my detector. So I want to compute the energy density using this formula. Okay, so we already have an expression for H, right? So we can compute H dot. Now, then we will get the 2-point correlation function of two of these H dots, okay? And so we need to add one more ingredient, and that is how to evaluate the 2-point function. And now we will do this, what I already announced the other day, right? Which is that we go from the volume average to the ensemble average, because we're considering a volume or a time large enough that is justified. And then we're going to use homogeneity and isotropy. Right, which for a cosmological source is just the cosmological principle. For an astrophysical source, it's just based on the fact that, okay, we have a lot of sources, right? And they will kind of average to something that we expect to be homogeneous and isotropic. Then later on, we may want to go back on this assumption, right? We may not want to always assume that this is isotropic, right? But if we have isotropy, then we can just use H lambda k, H lambda k prime, lambda prime k prime, 2 pi cubed delta lambda lambda prime. So this is just the orthogonality of the two polarizations. 2 pi is convention. Then we have homogeneity. So that means that we have this condition on the k's. Homogeneity. I'm not sure that's correct. And then isotropy means that we get a power spectrum here, and the power spectrum only depends on the absolute value of k. All right, this is isotropy. And if we have this, we're now ready to take the time derivative of this guy, plug it in here, do the 2-point function, and then plug that back in here. And all that together gives you now finally the energy density of gravitational waves evaluated today at tau 0 as 32 pi g to the minus 1. Then this term comes from taking the time derivatives. And then this comes from doing the 2-point correlation function, k squared dk sum over lambda p lambda of k. And then we get the transfer function squared. A squared of tau, a squared of tau 0. All right, so this is final expression for the energy density, where again, right, same as for the expansion, these are in some sense the primordial coefficients or the primordial power spectrum. And this is the cosmological history. So this is the total energy density in gravitational waves, which also means if you observe such a thing today, right, it's always what you observe, both if you observe a wave function or if you observe the energy density, it's always a convolution of whatever was your primordial power spectrum plus the transfer function. So usually what you do is you say, well, I know the expansion history of the universe. I just put in the cosmological standard model. And hence, if I observe something, I'm going to use this to learn about the primordial power spectrum. But you can also do it the other way around, right? If you're like super convinced that your model is the right model of the universe, right? So you say, well, I know what is this, right? Then you can also use this to constrain the cosmological history, right? So your model doesn't fit the data, you can say, well, let's change cosmological history, right? And make my model fit the data. A lot of people do that. But the fact is that kind of whatever you observe is always a convolution of the two. And then one last line here is that often, so this is the total energy density, right? So it's integrated over frequency. It's just one measurable thing, right? So from one measurable number, it's very hard to kind of disentangle all this information. However, typically you have access to more because typically you have access to energy per frequency bin, right? Because your detector has some frequency resolution. So you can write this as critical energy density for normalization, d ln k. Now we put this back in again. D rho ln k, d rho over d ln k, right? And maybe instead of k, we can put f, because frequency is usually the thing that you observe in a gravitational wave detector. So here I've done nothing, right? I mean, I've just rewritten this left-hand side in a complicated way, right? Taking the derivative and then doing the integral. But this thing, the reason I've done it is that this thing inside is what people call omega gravitational wave of f evaluated today. So this is the energy spectrum of gravitational waves. The energy spectrum of gravitational waves. So the energy per frequency bin normalized, or the energy per logarithmic frequency bin normalized by the critical energy density, right? And so that's the thing that tells you how much energy per frequency, right? So that's the thing you can predict in your favorite cosmological model, and then that's the thing you can compare to the experiment, which is measuring how much energy, how much strain amplitude, stochastic strain amplitude am I getting in the different frequency bins. Okay, questions? Tau is not the function. Tau is just time, right? Tau star is a function of k. Yeah, exactly. This is why we kept the index k on the transfer function. Yeah, so the definition, so it depends. It depends again if you're super horizon or sub horizon, right? So sub horizon, tau star does not depend on k, right? Tau star is just the time of the source. Super horizon, then the condition is that a star h, well, a of tau star, h of tau star is k. Or, I mean, this is tau star to the -1, right? So, well, in the sitter, let's leave it at that. That's the general condition. So this is what people call gravitational wave spectrum. Okay, any questions on that? Yeah. We'll get to that in the second part of the lecture. Good question. Not obvious. Okay, let me show you one example of what the spectrum looks like. Then we'll have a break, and then we'll talk about detection. So the example that I want to use is the example you've seen last week, right? Single field slow roll inflation. Are there still some questions? So what you've seen last week is this gravitational wave spectrum, right? So then often people put an H here, but there's also a lambda from inflation, which is the power spectrum of the tensor perturbation at horizon crossing, right? And then it stays the same, right? It stays frozen. So 2 over the Planck mass, H scale of inflation, right? Or to be precise, the scale of inflation of horizon crossing, 2k cubed. Okay? Hope that rings a bell. Quan said it should ring a bell. Or often people don't write it like this, right? Often people absorb the k cubed in the definition, and then you get what people often call delta t squared or at, which is just k cubed divided by 2 pi squared, sum over lambda p lambda. And this is the thing, this is what is constant, right? So the statement that single field slow roll inflation gives you basically a scale invariant spectrum, right? Under the assumption that the Hubble parameter during inflation is constant. That's a statement about this quantity. Does this ring a bell? You saw this yesterday, last week in some form? No. Okay, so you should have seen that both the scalar and the tensor power spectrum that you generate during inflation is at leading order scale invariant, right? And this is the tensor power spectrum, right? The scalar power spectrum is the one that is imprinted in the CMB, and when people say NS close to 1, right? That's scale invariant scalar power spectrum. Now we're talking about scale invariant tensor power spectrum. And then there's the R, right? The tensor to scalar ratio, delta S squared divided by delta T squared, right? Which is just the difference of the prefactors in this expression, and tells you how much the gravitational wave spectrum is suppressed compared to the scalar power spectrum. Good. I know, a week is long ago. I don't remember what I had for dinner yesterday, so but now what we want to do is plug this expression in here. Okay, because that's exactly what it is, right? This is a 2-point function of the gravitational wave at horizon crossing. So it's exactly the primordial power spectrum appearing here. So omega gravitational wave, evaluated today from inflation. We plug this expression in here, because it's scale invariant, right? Doing the integral becomes trivial. This k cubed cancels with that k cubed. And we get delta t squared. If you collect the prefactors, gives you a 12 k squared a 0 squared. Okay, so now I'm wondering where the k squared comes from. Okay, I need to think about where the k squared comes from, right? But not seeing it right now. But believe me, it's there. Yes? You think I'm missing a... You think this is D3K? Let me check, okay? Don't want to make a mess now. I'll check until, well, tomorrow by the latest. It could be, because I mean also from the time derivative, right, I would expect to get two k's down. Okay, I'll check until tomorrow. Let's not get hung up on this, because otherwise we have no break. A star to the 4, sorry, and now we have the transfer function, right? So A star divided by A squared. Okay, so modulo that straight power of k, which we'll figure out. This is the expression. Okay, and now we see we have one frequency dependence here, but we have also the implicit frequency dependence here. Okay, because this was, now we're really looking at a super horizon source, so we have this condition for A star. And now it really depends. It depends on, are you in, did your mode reenter during radiation domination, during matter domination, and this will change this factor. But one way of seeing, at least in some limits, what's going on, is we can rewrite this by multiplying this k down here with A star h square, right? So this is just 1. And now I have to take these factors and factor them back in here, so I get A star to the 4 h square, h star squared, h naught 4 h, A naught 4 h naught squared. And now you see one example is during radiation domination, right? So for modes entering during radiation domination, you know that h square, right, which is just the energy density during radiation, scales as a to the minus 4. So this term is constant. Okay, during radiation domination, this term is constant. This term is unity. This term is anyway constant. So what you expect for your gravitational wave spectrum So there's some period here where the thing is just constant, right? This is modes entering during radiation domination. Then at some point I have matter radiation equality. Before that, I have modes which scale as f to minus 2, right? So this you get by evaluating this a to the 4 h squared term in matter domination. And this is the usual story of inflation, that modes that are generated late in inflation, right? They cross the horizon at the end of inflation. They re-enter early, right? So they re-enter kind of in the early history of the universe. And these guys are the guys that enter at late times, so at large scales, right? That's the usual, the weird time counting of inflation, right? So large frequency means re-entered the horizon very late, right? Which means left the horizon very early, which means this is the late time matter dominated phase. This is the radiation dominated phase. And then here we have, well, whatever happened at the beginning of the radiation dominated phase, right? So here's reheating, and then what happened here, we don't know, right? It depends what is the equation of state during reheating, right? If the equation of state during reheating was also matter dominated, you would get another f to the minus 2 phase. If during reheating you had something crazy, right? get some kination domination, I don't know, right? Then you get something crazy here. So this part of the spectrum is relatively fixed because we understand the cosmological history at late times. Here we have uncertainty because we don't understand cosmological history at the end. And the CMB bound, right, comes here, right? So the CMB bound is at very large scales, low frequencies. So the CMB bound kind of tells you that here you have some limit, right? This limit tells you R smaller 0.1. And so that means whatever you do, this entire spectrum has to fit below the CMB limit. And now if you observe this, right, hypothetically, imagine you have a bunch of, very hypothetically, right, you have a bunch of fantastic instruments, right, and you can really measure really this curve, right, all along the curve. What would you learn? Well, you would learn the primordial spectrum, right? You would maybe also see, because you could observe it the entire time, right, you wouldn't just see what is my inflation potential at the CMB scales, right, but you can really map out the inflationary potential all the way. And because this is convoluted with the cosmic history, right, you would also see if anything happened in your cosmological history. In particular, if you had supersymmetry at 10 to the 10 GeV, you would expect to see a little bump here when the degrees of freedom change, right? You would also expect to see a little bump at the QCD phase transition, right, because the degrees of freedom change, right? So in principle, all that information is in here, right? In practice, to destroy your hopes immediately, right, this particular spectrum, right, the one of single field slow roll inflation, is close to impossible to see, right? Our current detectors are nowhere near getting to this sensitivity. And also, well, we expect to have astrophysical foregrounds which are significantly larger than this, right? So in principle, all the information is there. In practice, detecting it is a whole different story. There was a question up there. No? Question? This is, okay, this is not the n-effective bound. This is way better than the n-effective bound, right? So there's also a bound on the total energy density, right? That's somewhere up here, right? So there's also, that bound is there's also there, right? But here I'm really talking about the direct measurement of the tensor modes to the CMB, right? And that is on the scales of the CMB, so that is very large scales. So this is low frequency. Yeah. No, because it's by definition primordial, right? So that's really the spectrum that you generate during inflation, when really the universe, you just have quantum fluctuations, you don't have any structure formation yet. So then it's true, okay, it is true that here we've taken our universe, right, to just be FRW. Okay, we've expanded around an FRW universe, right? So what we're getting here is how any gravitational wave spectrum evolves in an FRW universe, right? If you have structure formation, you have lensing, right? You'll have, gravitational lensing, which you have for the photons, you also have for the gravitational waves, right? That will distort the spectrum you actually see in reality, right? The same as it does for the CMB. That will be a small correction in the sense that kind of structure formation is a small correction on top of an FRW universe. But yes, we're not perfectly an FRW universe, right? So all those corrections you would need to kind of factor in, but they're going to be tiny. Yeah. Right, then you would get, whatever, if here's BBN, right, then you would get something like that, right, and then it would evolve, whatever. Yeah. So in principle, you can map out the evolution of the scale factor, right, so the expansion history of the universe, all the way to inflation. In principle, right, if you had an instrument which could get down there, right? But there's still a difference between not being able to observe something because it's conceptually unobservable, right? And being able to not observe something because you don't have a good enough instrument, right? Or you're not good enough of doing foreground subtraction, right? That it depends, right? In Anson's words, right? Is it measurable within my lifetime? Is it measurable not at all, right? Here we're at the status that this is probably not measurable. This particular spectrum is not measurable within our lifetime, I would say, but it's not conceptually unmeasurable, right? And I'm giving you this example because it's a very nice example, because you've seen it last week, but it's not the most promising thing to go for if you're actually performing an experiment, right? And we'll talk about signals which we are more likely to see in the sense that they are larger signals, not in the sense that the models are more plausible, right? It's always going to be the balance of the two. Up, like this? Yes, kination domination. Right, kination does this. Okay, let's try and have a 10 minutes break. Yes. Okay. Yeah, so let me first just briefly confirm, right, that, yeah, we do need the, we do need the k cubed up there, right, because initially we had two d3ks from the two combinations of h. We lost one d3k with the delta function, but then from the two time derivatives, we got another k squared, right? So then we need k squared d3k, and then it matches with what we were doing with the energy density. Good, thanks. Okay. So with that, let me answer the question that was asked before the break, right? Which is, okay, so now we've computed now we know how starting from some primordial spectrum, right, be it during inflation or be it post-inflation, we can compute the spectrum of the energy density today. And now we still need to measure it. Okay, so how do we do that? So imagine you have an interferometer in your backyard. Okay, so you have at some point x0, you're emitting a photon along an interferometer arm with length L, direction small l, length large L, and you have a gravitational wave coming from some direction, right? And you now want to know what is the impact of the gravitational wave on this interferometer. Okay, so far, this applies to both the stochastic background or just a black hole and spiral. You just want to know, okay, how do I actually compute the response of the detector to an incoming gravitational wave? Okay, so the gravitational wave HAB. And I'll be using, yeah, so AB are just 1, 2, 3, right? Because I'm be going to TT gauge. And I'll also be dropping the TT indices, right? Because I don't want to drag them along all the time, but all of this is in TT gauge. Okay, and then we have an interferometer with the arm going in the L direction. So in TT gauge, we can now compute the proper time, right, that it takes for the photon to go from here to here. So that is just dt squared plus delta AB plus HAB del XA del XB. X is pointing in this direction, so we can write this as 1 plus HAB LA LB d lambda squared, where lambda is now just my parameter, my affine parameter parameterizing this length, right? So the position here, XA, is just lambda times LA, and lambda should go from 0 to capital L. Okay, just parameterizing the trajectory of the photon. So that's ds squared, right? Now I'm interested in ds, so I want to take the square root of this. So taking the square, instead of taking the square root, right, I'm just going to say, okay, well, I take the square root of this, right? So that would give me 1 plus 1/2 HAB LA LB in the limit of small h, right? So I square it again to get back the initial expression. But this thing here, right? This is basically, or just this alone, right? Is, if you want, delta S, right? So the shift in the proper time that the photon experiences between here and here due to the gravitational wave. Okay, if there were no gravitational wave, right, then you just get the, well, that it takes time L, right, to go from here to here. So, and this is, okay, so this is, remember that we said here we need TT gauge, right? Remember we said in the TT gauge, test masses don't move, right? So if test masses don't move, you may wonder, well, actually, how does LIGO work, right? If the mirrors are not moving, how is LIGO measuring anything in the TT gauge? This is how LIGO measures stuff in the TT gauge, right? The mirrors are not moving, mirrors are free falling, in this frame not moving at all, but the proper time that it takes for the photon to go from one mirror to the other does depend on the gravitational wave, right? And if the travel time depends on the gravitational wave, it means that the phase of the photon depends on the gravitational wave, and the phase of the photon is the thing that you're actually measuring in an interferometer. So with that, we can now compute the time delay. So this is the time delay experienced by the photon due to the gravitational wave at time t. And it's exactly that expression here, right? So 1/2 LA LB integral 0 to L HAB. Just integrate along the line of sight. And I have to evaluate my gravitational wave at whatever point I am, right? So at t plus s and x0 plus SL hat ds. Okay, so this is the time delay that a photon experience that is emitted at time t. Okay, and then correspondingly at time t plus s, it will be at position x0 plus s moving along that path. Now, we need to plug in the expression for the gravitational wave. So now I'm just doing detection, right? So now I don't care, for the moment, I don't care about all my cosmic evolution, right? I have a gravitational wave at this point in time, right? So I don't need to worry about scale factors. So I just do my Fourier expansion. Write this as d3k e to the minus ik, oops, I k x minus omega t, sum over polarizations. We have the polarization tensor, plus the Hermitian conjugate. I might have forgotten the Hermitian conjugate above, right? We need it, right? The gravitational wave should be real. Now, what we can do next is that we can take the Hermitian conjugate and we're going to rewrite it, right? So I'm going to write it explicitly. Take it away here, write it explicitly. And I'm going to, however, since I'm doing this in this d3k integral, I'm going to flip k to minus k. Okay, so I'm going to do complex conjugation and flip k to minus k, which means that here the first term actually stays the same, and only the second term changes sign. Okay, because I've done complex conjugation, flip k to minus k. In the second, then I have here, polarization tensors are real in the plus cross basis that we're using, right? So lambda is plus cross. So lambda plus, lambda cross, going to call it plus minus 1. So I just have the flipping of the sign in the argument. And then here I have h lambda star from minus k. Okay, why have I done this? I have done this so that I can now take the two things together. I can write e to the d3k, e to the minus ikx, sum over lambda. Now I use a property of the polarization tensors, and that is that e lambda a b of minus k is the same as lambda times e to the polarization of k. So meaning, if I flip the polarization tensor, if I flip the k vector inside the polarization tensor, I get the same up to a sign, right? And the sign tells me that the plus polarization is even, and the cross polarization is odd under parity transformation. Okay, you can check this explicitly by kind of explicitly constructing a basis vector around k, and explicitly doing the transformation, the parity transformations to see how they transform. So one way of doing it is, for example, you say, okay, I have k, right? And I have k and some other axis, say the k and the z axis. And then I define myself two vectors, right? One by saying I take the cross product of k, let me call u, is the cross product of k and ez. And then v is the cross product of k and u, right? So now k, u, and v form an orthonormal system. And now I can use u and v to construct the polarization tensors by basically products of u and v. And these polarization tensors will have exactly this property. And they will also have the property, of course, that they are orthogonal to k, and that the trace is unity. Okay, but that means that here we can just put lambda, sorry, here we just put EAB of k, and then what is left is e to the, from here, we have e to the I omega t h lambda of k, plus lambda e to the minus I omega t h lambda star of minus k. And this thing, for convenience, I will call h lambda of now t and k, right? So it's definition. And it's just a definition to be able to write this object in a bit more compact way instead of always having to drag along the Hermitian conjugate, right? It's just a way to kind of, I'm using that I know the gravitational wave is real, and I'm writing the Fourier expansion in a slightly unusual way just to ease the notation. You'll often see in the literature that people don't do it this way. Instead, they do a Fourier transformation where they have the df, right, or the frequency integral, going from minus infinity to plus infinity. Okay, that's the same thing. It just means that kind of here, they're not flipping the direction of k, right, but they're summing this term and this term by saying that they have a frequency going from minus infinity to plus infinity, right? It's the same thing, and there's nothing physical about a negative frequency, right? It's just a compact way of writing a gravitational wave. Okay, but we need to do it once because otherwise all the following computations make no sense if you don't know what this object actually is. And here, let me just maybe give you the properties here, right? So here we know E lambda AB of K contracted with K has to be 0 because it's orthogonal. And we also know if we have two of these guys and we contract them, it should give you unity if you have the same polarization and 0 if they have opposite polarization. Okay, and so now we plug this expression, right, in here, and we compute the time delay. So integral d3k, this is nothing changing, sum over polarizations, 1/2 LA LB. We can take the e to the minus I k x factor outside of the ds integral, 0, right? Now we have the ds integral going from 0 to L. And here we have now, because now we're putting this argument in here, right? So the x0 part we can pull out. The SL part remains inside the ds integral. So we have e to the minus I omega s KL. And then we have this coefficient here, H. Oh, where did my, okay, I forgot the polarization tensor. Okay, also the polarization tensor does not depend on S, right? So it can go out, right? So we have some E, A, B of K and lambda here. Okay, but this means that this integral is not too hard, right? We need to perform the integral over this guy. This guy is defined here. So that's an integral we can perform. And what you get is IL e to the I omega t 1 minus e to the I omega L 1 minus KL divided by omega L 1 minus KL. Okay, so I've expanded with a factor L on top and below. The reason is that this L is just kind of the trivial L, right? Saying that, okay, the longer the stretch, the longer you will get the time delay. And this combination, omega times L, right? So the gravitational wave frequency with respect to the size of the detector is a useful dimensionless quantity to understand the different regimes. So okay, so what does, plus HC. So, and also there has to be the, sorry, important, right? We have to add, of course, there's still the h lambda of k plus h3. Okay? So what does this tell us, right? So this tells us we have an integral over the gravitational wave vector, right? We have a sum over polarizations. Then we have some geometric function which depends only on the incoming gravitational wave and the geometry of the detector. And then we have the amplitude of a gravitational wave. So this entire thing here is called response function, right? So it's something which depends on the polarization, depends on k, and depends on the geometry of the detector. And it tells you how your detector responds to an incoming gravitational wave. Okay, now we have a very simple detector. We have just one photon going along in one direction. You put a more complicated detector, right? This thing gets more complicated, but not conceptually more complicated, right? You just, and now you can add more arms, right? By just summing more time delays. Add more arms, more detectors, right? But fundamentally, it's always going to have this shape. So this guy is response function. So we can already understand some properties of this guy. So one, you see this term, right? You have L, the arm, direction of the detector arm, constructed with a polarization tensor. This means if you have a gravitational wave incoming along the arm of the detector, right? So if K is aligned with L, then here you just have the product, you have K contracted with E, and then since this thing is orthogonal, right, it's going to be 0. So the response is going to be 0 if your gravitational wave comes along the arm of the detector. So F lambda of K is 0 if K is parallel to the detector arm. We can also look at limits, right? I said this is a good quantity to distinguish different limits of the detector. So we can consider the limit small frequency limit. Omega is much, much smaller than 1 over L, right? So in this case, you can expand, right? You can drop this term up here. You expand in omega L. What you get is that the response function of K is constant in K. Right, constant in the absolute value of K, right? Which means it does not depend, it still depends on the direction of the gravitational wave. It no longer depends on the frequency of the gravitational wave. And that, in fact, is the limit that LIGO is in. Right, this is the LIGO limit. And in the LIGO limit, the response function is just constant. You can also look at the opposite limit. So if omega is much bigger than 1 over L, then what happens here is that this term here, this omega L term, if I form the 2-point function, right? So in the 2-point function, I will look at 2 of these objects, which means I will get 2 of these response functions, which means that I will be evaluating 2 of these exponentials, but at different points of space. And then what happens is that they become uncorrelated, right? So it's basically simply because I'm looking at the gravitational wave at 2 points which are so far away that the gravitational wave is oscillated so many times in between that I lose correlation between the 2. So in this case, this e to the I omega L 1 minus KL term drops in the 2-point function, right? Not here, in 2-point function. And that is, in fact, the PTA limit, pulsar timing array limit. And this term that we drop is called the pulsar term. right? And hence you're only, basically in this integral, you're only, in pulsar timing array limit, it's only the lower integration boundary that contributes to the observable. The upper integration boundary does not contribute. Okay, so this was the response function for a single arm, right? And we still haven't really talked about stochastic backgrounds here, right? This is just completely general for any gravitational wave. Now, let's get concrete. Let's look at a concrete detector. And really an interferometer, so LISA or LIGO. And then let's see how we can use this to actually measure stochastic backgrounds. LISA, LIGO, that type of experiment. So now our setup gets slightly more complicated. So now we have a detector with two arms, right? So this still kind of measures the arm directions, either this way or this way. We have one test mass, 2, 3. We have an incoming gravitational wave. And now what we need to do is we need to compute not only the photon going from here to here, right? But we need to compute the photon going from here to here with the return trip. And then we need to compute the photon going from here to here, bouncing back. And then we need to compute the difference in the time delay of this photon versus this photon, right? And that is the observable of LIGO. Yes? So omega, yes. So omega, yes. Omega is, k is the absolute value of k vector. No, because I'm just looking at the response function, right, which is the integrand. Right? This is on the outside. Yes, okay, but still, okay, it's true that within LIGO, right, you're not sensitive to exactly one frequency, right? There's a range of frequency, but that range is relatively small. Right? You have to compare, I mean, the frequencies that LIGO is sensitive to is 100 hertz plus minus 1 order of magnitude. And L is the size of the detector, right? The effective size of the detector. We'll get to the sense that we're not there yet, right? We're just comparing the length of the arm. Here we're just saying I compare the length of the arm length to the regime where I know that the detector is sensitive. Why the detector is sensitive there, right? We will get to in a second. It's not just one over the arm length. Okay, so we need to do return trips of the photon. So let me call this S12, signal in the 1-2 arm. So what is this? We need to sum the time delay accumulated when I go from 1 to 2, right? So I'm going to now look at the photon that I observe back in my interferometer at time t, okay? So that means I'm looking at the time delay going in the 1-2 direction of a photon emitted at t minus 2L, plus the time delay going in the other direction emitted at t minus L. Plus, I can have noise. Okay? And so now we need to basically take this expression for the time delay, or better, this expression for the time delay, right? Shifted by the corresponding amount of t, and take into account, right? Let's still call this point here 1, we call x0, right? So this guy will be evaluated at t minus 2L, and at, let's say, x0 to 0. But here, we're going to, with the other point, right? So we have to set x0 to L, 1, 2, L, okay? I'm just going to call this L because we're just doing one arm for now. And okay, I go through this exercise, right? I get, not surprisingly, right? I mean, I'm going to get the same structure because I'm just going to get this term twice with the arguments shifted a bit. So what I'm going to get is this factor of L can just go to the outside. dgk, sum over lambda. Again, a response function, which is going to now look a bit more complicated. And in particular, it's going to look like 1/2, so the prefactor stays the same, 1/2 LA LB. Promise you this is the last formula of this type that we're writing. Then we have it, I think then we've got it. Polarization tensor times e to the minus I omega L over 2. So now we're doing the first term. 1 plus KL sine omega L over 2, 1 minus KL. So actually, it simplifies a bit when you do the return trip. Because we are the opposite direction, you have the Hermitian conjugate, and it makes your life a bit easier. And now plus, I have the other term. So now I have to shift x0, right? And I have to shift L goes to minus L, right? So I have to also use L goes to minus L here because I'm going the other direction. So I get e to the I omega L over 2, 1 minus KL sine omega L over 2, 1 plus KL omega L over 2, 1 plus KL. Okay, I mean, roughly you see what's happening, right? So you see, okay, you see this term more or less corresponds to this term with L flipped to minus L, right? So it's just a return trip. I've kind of factored out here, yeah, I've combined the term with the x0 and the term with the x0 to 0 in the two terms to factor out a factor, which then drops in late in the computation. And again, so we see, and now we even see it more explicitly. You can explicitly check if you just take this term and you take omega L much smaller than 1, you will get 2. And that is the LIGO limit. And also, if you're not in that limit, right, I mean, this sine x over x, right, is just something like this, right? So you see here, this is the LIGO limit, right? You're here. And if you have large omega L, right, what happens is that as your photon goes from here to here, you're kind of going over many, many oscillations of the gravitational wave, right? So your phase gets shifted back and forth and back and forth and back and forth. And so you lose sensitivity. Okay, so kind of you lose sensitivity if you go in this limit, right, where omega L is larger than 1. And in the low frequency limit, you recover what, from what we get is what is the LIGO response. And this is a name, right? This is the single arm detector response. Okay. So now we can do response to stochastic backgrounds. So this was one arm, right? But now going from one arm to two arms is trivial, right? So let's say we have an interferometer alpha, right, then the total response, right, so the signal alpha will just be a signal in one arm minus signal in the other arm. Right, so this is the time delay we get here. Then we do the exact same thing. We get the time delay we get here. And the total response, right, is just one minus the other. Okay, so now we want to know what is the response to stochastic background. Okay, response to a transient signal, well, you know, like, okay, you can really directly, for a transient signal, you would directly measure this thing, right? So you would directly measure the time delay. You would measure, your data is really a data stream in time. And you will literally kind of see the waveform of the merger, right? Because you will literally see a linear response to the incoming gravitational wave. Now, for stochastic backgrounds, we can't do that, right? The linear response, it's going to be zero, right? Because we're averaging over different phases, different frequencies, different waves, just give zero. So if we would compute something like this for a stochastic gravitational wave background, right, it will be zero. For a transient signal, it's a perfectly fine thing to compute. So what do we need to compute? I mean, we already anticipated that the energy density is the thing that actually has the physics. So what we need to compute is the two-point function. Okay, so we need to compute, we get the signal, and we autocorrelate it either with itself, or we autocorrelate it with another detector. So if we autocorrelate it with itself, we just get the two-point function of this guy, right, after plugging in this guy. So that will be schematically d3k sum over lambda. We will get the two-point function of HH, right? So this is just P lambda of K in our notation. And then we will get the response function. So we will get F lambda 1, 2, right? Which is this guy, minus F lambda 1, 3 squared. Right, so it's just a linear combination of the two single arm response functions. Plus, we will get the noise. And here's the problem, right? So the problem is that this, okay, it's non-zero, right? It's something we can measure. However, it's really completely degenerate here with the way the noise shows up. Okay, we just have a two-point function of the signal, and we have a two-point function of the noise, and it's going to be very hard to distinguish one from the other. So what we do in LIGO, for example, to counter that is we look not at the autocorrelation, but the cross-correlation. So we take two interferometers, alpha and beta, right? LIGO Hanford, LIGO Livingston, and we cross-correlate the two detectors. So then what you will get, right, schematically, you won't get this same thing squared. You will get, let's call this thing is F lambda alpha, right? The response of the detector at location alpha. And so you will get L squared d3k sum over lambda P lambda of k F lambda alpha of k F lambda beta of k. So this is the autocorrelation, right? This is the cross correlation. In both cases, this is kind of your gravitational wave spectrum, right? So your signal, right? This is your detector response. And for example, in LIGO, right, if you do the cross correlation, right, this thing has a name. It's called the overlap function. And the reason that it's called the overlap function is that you have, so in principle, if you have two detectors far away, right, you can hope that the noise is uncorrelated, right, which is why here we dropped the noise term. Not entirely true, right? If you have a lightning strike which hits the electricity grid of the US, it gives a noise in both detectors. But in an ideal world, if you have the detectors far apart, the noise is uncorrelated. However, notice that here in the up there you see it, right? In the expression for the time delay, we had the e to the minus ik x naught. Okay, so if I'm just looking at one detector, I can just set x naught to 0. If I have two detectors, I cannot set both of the x naughts to 0, right? So I will get here something in this overlap function that goes as e to the ik x of detector 1 minus x of detector 2. And I'm integrating over k. So kind of the same thing is happening that is happening here, right? If my detectors are far apart, I'm integrating over a rapidly oscillating function, and I'm losing sensitivity. So I want to put my detectors far apart to reduce the overlap in the noise. But if I put them too far apart, I'm also losing sensitivity in the signal because they're no longer well correlated for the signal, both of my detectors. Okay, any questions on this before we draw a few plots? How big is what? How big is what? So in the LIGO limit, you're really here. It's constant.
Yes, but if I look at all the frequency range.
No, but you cannot because you have no sensitivity.
No, I'm not talking about all the frequency range of the gravitational waves.
Yeah.
But one seen by LIGO.
It's very good. You're very deep inside this limit.
So overall,
I don't know, percent or so, right?
okay.
So you want to know how big is omega L? Okay, so we will compute on Friday. But basically what you do is you say this is 100 hertz, right? And this is 4 kilometers, right? Times about 100. And 100 is the finesse of the cavity, right? Because actually LIGO is not quite like this, right? But the photon bounces back and forth and back and forth, back and forth, right? So that's the computation you need to do. You just need to now convert kilometer to hertz and you have the answer. Here, maybe here. Okay, let me, since we're already at 12, so let me finish up the stuff on the interferometers, and then the pulsar timing arrays we move to Friday. So this is the general expression, right? Now let's simplify our life, and let's look at the autocorrelation of an isotropic, unpolarized, stochastic gravitational wave background. Okay, that's more or less the simplest thing you can do. So then, what does it mean? Unpolarized means that we can take this outside of the sum. And isotropic means that basically we write this as k squared dk d omega, right? And then we can, moreover, take this guy out of the d omega integral, right? And we just leave it inside the k integral because we're not going to assume that it's scale invariant. We're just going to assume that it doesn't depend on the direction. So then what we get for the autocorrelation is we're only left with the k integral. That's the only integral way on the outside. Then, okay, I'm going to write this again with, going to absorb the k cubed factor by writing the delta t instead of the pk. because then we see directly what the scale invariant signal does. But this could, in principle, still depend on k. Then we have the sum over lambda, the integral over the omega, and the response function. Okay? So this is nice, because this is purely geometry. Right? So this is something that does no longer depend on my signal, and this is something I can just compute. Right? If I know the detector, I know the arm length, I know the angle between the arms, there's no more dependence on the gravitational wave here. Right? I can just compute, and I will get this as a function of k. And so we can compute. This is the detector response. This is the signal. This is the detector response. And so if we take the example of LIGO, right, so really we have a right angle here between the two arms. You will get for the log of this expression here something that just looks, starts at 3 over 10, is constant. And then when omega L here is unity, it starts to decrease and wiggle a bit. Okay, and then in LIGO, we're really in this limit, right? So the response is just this constant value. LISA, right? For LISA, we would be in the limit. I mean, okay, the value here changes because it's no longer 90 degrees, it's 60 degrees, but it looks pretty much the same. And for LISA, we would be more or less around here, omega L around 1. So we actually have a frequency dependence of the response. Now you can ask, well, why is LIGO only measuring over here, right? I mean, why is LIGO not measuring over the entire frequency band? And that now gets back to the question of, well, how do I know where is the detector sensitive, right? So there's two aspects to where detector is sensitive. One is how large is the response, right? The larger the response, the better. The other is the noise, right? Because the larger the noise, well, problem, right? So because here, in principle, we still have the noise term. And so to estimate the noise, we look at what is called the signal to noise ratio, SNR. And that is roughly given by the duration time of the experiment, integral over frequency, whatever is my signal, right? So it could be the autocorrelation or the two-point correlation, squared, and then the autocorrelation of the noise in each detector, and then the square root of the entire thing. And basically the statement is, if the signal to noise ratio is larger than 1, you can detect it. If the signal to noise ratio is smaller than 1, you cannot detect it. And so then you have to combine, so this response function, right, together with the amplitude of the gravitational wave gives you the signal part. And now you need to know about the noise, right? So you need to know what type of noise sources are there in LIGO, are there in LISA, and in which frequency range do they contribute how much. And if you combine that information, then you actually get to the point where you can draw a sensitivity plot, right? So oftentimes people draw them in terms of strain over frequency. Since we're talking about cosmological backgrounds, we can draw them in omega in terms of frequency, and you will get typically something like this. Okay, so these wiggles here are exactly these wiggles here, right? So on the high frequency side, you lose sensitivity because your response function is decreasing. And on the low frequency side, you typically lose sensitivity because you have a bunch of noise, right? In LIGO in particular, below 1 hertz, you have all the seismic noise, and it's completely impossible to make a measurement. Okay, so the combination of where your experiment is sensitive is a combination of what you know about the noise and what you know about the response function. And basically on this line, more or less, right, you have SNR is 1 or maybe 10. And now if I have a signal which is here, right, roughly I can detect it. If I have a signal which is here, I cannot detect it. That is the statement. And now we've really also included the noise component, not just the signal component. So just in words, so here we assumed an isotropic source. right? And also earlier when I said, okay, we do the two-point function, right? We're going to assume an isotropic source. Nobody forces me to assume an isotropic source, right? In particular, say the astrophysical background from white dwarf mergers in the galaxy is going to be anisotropic because there's going to be more in the direction of the galactic center and less in the other directions. So nobody obliges me, right, to take this out of the omega integral, right? I can also keep this guy, right, inside here, right, and say, okay, fine, it has an omega dependence. And then what I would do is I would do an expansion in spherical harmonics or something, and I would get response functions which then don't only depend, so this guy, right, is basically depends on alpha, lambda, and k, right? And now I would also get response functions if I do an expansion, if I keep the omega dependence, I would get response functions because I cannot perform the integral over this guy separately because I need to have this unknown part. So I would do an expansion of spherical harmonics and say this, well, I get a response function for each spherical harmonic. Okay, and then I can say, okay, whatever, then my total observed signal is again the convolution of my signal plus the response functions. I know all my response functions, and now I can see how big is my sensitivity to the different multiples of the signal. And then you get things like that for LIGO, for example, we stay in this picture, the response function before doing this, the omega integral, is something like this dipole type thing, right? So LIGO is particularly sensitive to gravitational waves coming along this axis, right? And less sensitive to other gravitational waves, right? So I can use the anisotropy of the response function to kind of map out what is the directionality of the signal. Though it's not good, right? Don't expect to be able to do L equal 1,000, right, as with the CMB. If we can get up to L equal 10, right, that would be very non-trivial, right? Because these response functions are very wide angle, right? It's not, you can't get something super fine-grained with gravitational wave experiments. They're not, they do have some sensitivity to directionality, but it's very mild. So you can only, to some very limited extent, get information. Same with polarization, right? You're not obliged to assume it to be unpolarized, right? You can also just not take this out of the sum, right? You just leave it inside. And then same here, right? You don't perform the sum, you just keep the response function to the different polarizations. And then you can get sensitivity to the different polarizations. And so that's how you hope to map out information on the stochastic background, right? So you can kind of, with this, you get some frequency dependence, right? And then kind of you can also get some limited, so you get some frequency dependence, so you can hopefully map out the frequency dependence of omega. And then you can also kind of hope, since the response is polarized and it is anisotropic, you can hope also to map out properties such as polarization and such as directionality of the stochastic background. Okay, I think that's more than enough for today. Let's stop here.